For thousands of years, light was simply how we saw the world. It was a passive tool used to push back the dark. But in the 21st century, we turned light into a chisel, a hammer, an industrial weapon sharp enough to carve distinct canyons into silicon, pushing the very boundaries of where physics allows matter to exist. This is Fab D1X. It is more than just a factory. It is the single most expensive construction project in the history of Oregon. Inside these walls, the air filtration is so aggressive that a sterile hospital operating room looks filthy by comparison. The floor floats on massive concrete blocks, separated from the earth, so that a truck driving on a highway miles away will not shake the room. It is April 2024, and inside these crates sits the most complicated machine our species has ever engineered. It weighs 150 tons. It traveled 5,000 miles, dismantled into 250 separate containers, because no single aircraft was big enough to carry it whole. It costs $380 million. For 30 years, Intel wore the crown. They didn't just follow Moore's law. They wrote the rules. They enforced the pace. But success made them comfortable. And while Intel stood still, a Taiwanese foundry called TSMC didn't just catch up. They sprinted past. By 2024, the failure was obvious. Intel's chips were running hotter, slower. The manufacturing dominance that was the birthright of the company had completely evaporated. The investors were angry. The wolves were at the door. But here, in this rain-soaked plant in Oregon, a gamble was being unloaded from a truck. A machine that pushes physics to the breaking point. A machine using light so powerful that air itself blocks it, forcing the work to happen in a total vacuum. A machine that Intel paid billions to secure before anyone else. This is the story of the TWINSCAN XE. The story of how Intel bet its life on the laws of optics. And the story of how the United States government found itself owning 10% of a silicon giant. To understand why a publicly traded company would spend nearly $500 million on a single tool, and why they would corner the market to buy every single one that exists, we have to look beyond the balance sheet. We have to look at the fundamental hard limit of the digital age. We have to talk about the wavelength of light. For 50 years, the rules of the game were simple. Make the transistor smaller. Pack more of them onto the silicon. Get more computing power for less energy. This is Moore's law. It is often cited as an economic observation, but it is driven entirely by physics. If you shrink the switch, the electron has less distance to travel. It switches on and off faster. It generates less heat. But around 2019, the industry hit a wall. A physical, concrete wall. The features engineers were trying to print on the chips were becoming smaller than the wavelength of the light used to print them. Imagine trying to draw a hyper-realistic portrait using a fat, permanent marker. It is impossible. The lines bleed together. The image blurs. This is called the diffraction limit. The industry's solution was a marvel of engineering called extreme ultraviolet lithography, or EUV. This involves light with a wavelength of just 13.5 nanometers. To call it light is almost misleading. It is practically a soft X-ray. It doesn't exist naturally on Earth. To create it, machines must fire a high-power laser at a falling droplet of molten tin, vaporizing it into plasma twice, 50,000 times a second. It took ASML, the Dutch company that holds the monopoly on this tech, 20 years to perfect it. It saved the industry. TSMC embraced this complexity. They mastered standard EUV. They used it to print the chips in your iPhone, your NVIDIA GPUs, and the accelerators training ChatGPT. They bought the machines, tweaked the chemistry, and achieved high-volume domination. Intel hesitated. They looked at the price tag of EUV and blinked. Instead of upgrading, they tried to squeeze life out of the old deep UV technology using a complex trick called multi-patterning. They tried to draw that fine portrait by using the fat marker 3 or 4 times, layering the ink to create edges. It was a nightmare of alignment. It destroyed their yield rates. It was a miscalculation of historic proportions that cost them the crown. So, when ASML announced the next generation, High-Numerical Aperture EUV, or High-NA, Intel was done hesitating. Pat Gelsinger, Intel's CEO, made a decision that bordered on reckless. He moved to lock down the initial shipments before his rivals could react. He decided Intel would not be a fast follower. This time, they would be first. But why? Why spend $400 million on a scanner when TSMC is profitable with the old ones? To understand that, we need to look at the Rayleigh criterion. It is a simple formula, but it dictates the economics of a trillion-dollar industry. This visual explains the gamble. Resolution, the size of the smallest thing you can print, is determined by the wavelength of light divided by the numerical aperture. We cannot easily change the wavelength. 13.5 nanometers is already incredibly difficult to generate. So, we have to change the aperture. We have to widen the lens. We have to capture light from wider angles to sharpen the image. By moving from an aperture of 0.33 to 0.55, Intel can print features that are 1.7 times smaller in a single pass. That implies a 2.9 times increase in transistor density. It means packing nearly 3 times as much logic into the same square millimeter of silicon. In this industry, density is destiny. But achieving that density required ASML to break the machine. To redesign the optics with massive anamorphic mirrors that distort the light to make it fit. And for Intel, receiving this machine was just the beginning of the pain. Moving a TWINSCAN XE5000 is not like moving a piece of furniture. It is an operation closer to transporting a nuclear warhead. The machine is so sensitive to vibration that each of the 250 crates is equipped with internal G-force monitors. If a truck hits a pothole too hard, the warranty is void before the crate even opens. It travels in a climate-controlled vacuum, protected from the very atmosphere it will eventually inhabit. Fab D1X didn't just need to clear some space. The building had to be surgically altered to accept its new organ. The ceiling height had to be raised to accommodate a machine the size of a 3-story house. The floors were reinforced with tons of steel to support the 150-ton dead weight. Why such mass? Because the heart of this machine is a set of mirrors built by Zeiss in Germany. These aren't standard glass. They are crafted from a specialized glass ceramic material designed to have zero thermal expansion. If the temperature inside the machine changes, the mirrors do not expand. They do not shrink. They stay perfectly, terrifyingly still. They are polished to such an extreme degree of flatness that if one of these mirrors were the size of the Earth, the tallest mountain would be less than the width of a human hair. The cost of this single installation is staggering. $380 million for the hardware, millions more for the logistics, millions more for the facility upgrades. But the real cost, the one keeping executives awake at night, is the opportunity cost. Pat Gelsinger calls this the angstrom era. An angstrom is 1/10 of a nanometer, the scale of individual atoms. He declared that Moore's law was not dead, but merely waiting for a machine precise enough to manipulate matter at this scale. By securing the first high-NA scanners, Intel wasn't just buying a tool. They were buying time. They were attempting to trap TSMC in the past. The logic is brutal but simple. If Intel has the high-NA machines and TSMC does not, Intel can print the smallest features in a single pass. TSMC, relying on the older low-NA machines, is forced to use multi-patterning. Multi-patterning is the bane of a semiconductor engineer's existence. Imagine you need to draw a grid of lines so dense that your pen is physically too fat to draw them side by side. So, you draw every other line first. Then you move the paper a microscopic amount. Then you draw the lines in between. Then you align it again. And again. This technique is known as litho-etch. It works. TSMC has become brilliant at it. But it is an economic killer. It takes twice as long, or 3 times as long, to process a single wafer. It destroys cycle time. And in chip manufacturing, time is yield. Every time a wafer goes back into the scanner for a second pass, you introduce a chance for a defect, a speck of dust, a nanometer of misalignment. High-NA promises to fix this. 1 exposure, 1 layer. Perfect, sharp lines printed in a fraction of the time. It sounds like the Holy Grail. But there is a catch. A massive, physics-defying catch that ASML and Intel don't like to advertise. And it has to do with the shape of the light itself. To understand the trap Intel has set for itself, we need to look inside the machine. In a standard EUV system, the 0.33 NA machines, the light hits the mask, the blueprint of the chip, and reflects off it at a relatively shallow angle. It then goes through the lenses and hits the wafer. But to get to 0.55 NA, To get that wider cone of light that gives us the resolution, ASML had to make the mirrors bigger. Much bigger. And they had to change the angles. Here lies the problem. EUV mirrors are not like bathroom mirrors. They are Bragg reflectors, stacks of molybdenum and silicon layers. They work by interference. If light hits them at too steep an angle, the reflection fails. The light gets absorbed. The image goes dark. So, ASML was stuck. They needed a wider angle to get the resolution, but they couldn't reflect the light at that angle without losing the image. Their solution? Anamorphic optics. This is the critical innovation and the critical curse. In the old machines, the lens would shrink the image on the mask by 4 times in both directions. A perfect square reduction. A 4 times reduction in width. A 4 times reduction in height. But in high NA, that wasn't possible due to the reflection angles. So, the XE5000 shrinks the image by 4 times in the horizontal direction, but by 8 times in the vertical direction. It squeezes the image. Look at the visual. Standard EUV gives you a full field on the wafer, 26 mm by 33 mm. But high NA, because of that 8x squeeze, you only get half the height. You get a half field, 26 mm by 16.5 mm. This sounds like a minor detail. It is not. It is a catastrophe for chip design. Modern high-performance chips, the AI accelerators from NVIDIA, the server CPUs from Intel, are huge. They are often at the reticle limit. They take up the whole 33 mm. If your machine can only print half that size, you have a problem. You have to print the top half of the chip, then move the wafer, then print the bottom half, and you have to stitch them together. Stitching. It sounds like sewing, but in nanolithography, it is a nightmare. You have to align 2 exposures with an accuracy of less than a single nanometer. If you are off by a hair, the wires don't connect. The transistor is cut in half. The chip is dead. This creates aberration sensitivity. It creates interface roughness. It introduces new electromagnetic effects at the mask level. Intel has to simulate all of this. They have to redesign their chips to be stitchable. So, Intel spent $400 million to get a machine that is sharper, but half the size. They are betting that they can master the stitching. They are betting that the complexity of stitching 2 clean exposures is still less than the complexity of doing 4 or 5 exposures with the old machine. It's a calculated risk. But their main rival, TSMC, they looked at this physics problem. They looked at the price tag, and they said, no thanks. Building a semiconductor foundry is the most capital-intensive undertaking on Earth. It is a poker game where the blind, the minimum bet just to sit at the table, is $20 billion. You have to spend that money today to build a factory that might produce a working product 5 years from now. This is CapEx, capital expenditure. And in the chip wars, CapEx is the killer. Intel's CapEx wasn't just high, it was out of control. They were simultaneously breaking ground on megafabs in the Arizona desert, in the cornfields of Ohio, and in Magdeburg, Germany. They were filling these empty shells with concrete pedestals waiting for $380 million high NA machines. But the revenue wasn't there to back it up. The foundry division, the manufacturing arm of the company, was hemorrhaging money. It was reporting operating losses in the billions, quarter after quarter. By 2025, the Gelsinger era was over, but his ghost remained in the machine. Lip-Bu-Tan didn't rewrite Gelsinger's playbook, he ruthlessly enforced it. He finalized the split Gelsinger had started, turning Intel Foundry into a walled-off mercenary, totally distinct from Intel's design teams. The goal remained the same, to be a factory for everyone. But under Tan, it wasn't just a vision, it was a mandate. They would build chips for Apple, for NVIDIA, for Qualcomm, even if it meant helping the very enemies that put them in this hole. But the customers were paranoid. Why would Apple hand over its most secretive blueprints to Intel, a company that competes with them for the laptop market? It's like asking your main competitor to hold your wallet. And more importantly, could Intel actually deliver? The industry was watching the 18A node, the manufacturing process immediately preceding high NA. It was supposed to be the proof of concept. But rumors of yield issues and delays made the Silicon Valley giants keep their distance. The situation spiraled from a business problem to a national emergency. Intel is not just a corporation. In the eyes of the Pentagon and Washington, D.C., it is a strategic asset. It is the only American company with even a theoretical chance of manufacturing leading-edge logic. If Intel collapses, the United States becomes 100% dependent on Taiwan for the silicon brains that run its fighter jets, its power grids, and its AI data centers. And with geopolitical tensions boiling in the Taiwan Strait, with the People's Liberation Army conducting blockade drills around the island, a total reliance on TSMC was a risk calculation that the White House could no longer accept. In August 2025, the unthinkable became reality. Wall Street turned off the tap. The market refused to fund Intel's cash burn any longer. The company wasn't just losing value, it was running out of runway. So the United States government, citing the national security provisions of the CHIPS Act, stepped in. It was not a bailout, it was a buy-in. The government took a 9.9% equity stake in the company. Not a grant, not a low-interest loan. Ownership. For the first time, the US taxpayer became a direct shareholder in the means of production. It was a terrifying, necessary lifeline. A direct injection of sovereign capital designed to keep the lights on in Oregon and the high NA dream alive. But it changed everything. The last stand for Moore's Law was no longer just a corporate strategy. It had become a government black project. So, here we stand. It is late 2025. The US government is watching. The bondholders are watching. The entire global electronics supply chain is holding its breath. And finally, the machine is running. The node they are ramping up right now, the one entering high-volume manufacturing, is called 18A. This is the dress rehearsal. It proves the transistors work. It uses standard EUV tools. But the real prize? The last stand? That is the node called 14A. That is the moment the high NA scanner is finally unleashed to its full potential. Intel claims 14A will deliver a massive 15 to 20% jump in performance per watt. To achieve this, they are deploying a holy trinity of new technologies simultaneously. First, Ribbon FET 2. This is the next evolution of the gate-all-around transistor. In the old days, the control gate sat on top of the channel like a bridge over a river. Now, the gate wraps around the channel completely. It surrounds it. It strangles the electrical flow. This gives the engineers absolute control. It shuts off power leakage instantly. It boosts performance. Second, Power Direct. This is known in the industry as backside power delivery. For 50 years, chip designers had to feed power to the transistor from the top, weaving high-voltage wires through the delicate maze of logic gates. It was messy. It created interference. It was like trying to fill a bathtub by running a hose through the chimney. Now, Intel drills the power straight through the back of the silicon wafer. It is like rewiring a house, so the power lines come up through the floorboards instead of the ceiling. It cleans up the signal. It eliminates voltage droop. It allows the logic cells to be packed tighter than ever before. Third, turbo cells. These are specialized blocks of logic designed to sprint. They allow the chip to identify which parts need to run at maximum frequency and which parts need to save energy, optimizing the mix within a single block of silicon. This is the weapon Intel hopes will finally slay TSMC. The 14A node is the justification for the $400 million machine. It is the reason for the stitching nightmares. It is the reason the US government felt compelled to buy a stake in the company. But the haunting question remains: is it too late? TSMC is already quietly working on their own high NA machines for the future. But they played it safe. They let Intel take the risk. They let Intel break ground. They let Intel pay the tuition to learn how to use these tools. Intel's $400 million scanner is a marvel of human engineering. It is a testament to what our species can do when we push physics to the absolute edge. But as a business strategy, it is the ultimate high-wire act. If 14A succeeds, Intel reclaims the throne. The US government's investment pays out. The gamble works. Moore's Law survives for another decade. But if it fails, if the stitching creates defects, if the yield is low, or if the costs are simply too high, then that machine in the rain in Oregon becomes the most expensive tombstone in the history of technology.